So I want to tell you a bit about our recent work, and more precisely about recent attempts to try to construct perturbation series within diagrammatic Monte-Carlo, but starting from new points, starting from different trailheads to try to address this strongly correlated problem. So this is the outline of my talk. In the beginning, I'll just tell you exactly how we do diagrammatic Monte-Carlo, with a focus on where exactly we stand, so what it is we can do and what are the limitations of the approach so far. And my focus here and during the rest of the talk will always be on the Hubbard model. And maybe I should say now before I forget, but whenever I'll talk about units, I'll work in units of the nearest neighbor hopping T. So that will be my convention if I forget later. And I'll discuss a bit about the role that the starting point of the construction of the perturbation theories, what that starting point may have, what are the consequences for this. And then I'll discuss two starting points that we explored. One is very close to what Felix has presented just before, to start from an RPA-like solution. Another one, which we call Renormalize Determinants approach, is something that lets quite a bit of freedom on the non-interacting propagator that you start from. Then I'll show you some results and conclusions with a focus on what is the structure for the observables you're interested in, as seen in the complex plane, and especially what the pole structure, how it may have changed as we went from different starting points. So the two mountain climbers behind this work are really Fedor Szymkowicz at École Polytechnique and Collège de France here, and Ricardo Rossi here at CCQ, Flatiron. They pretty much did everything except present these slides. Also benefited from many useful discussions over the years. For example, yet another mountain climber, Alice Moutenay, then usual suspects like Olivier and Antoine. And these days I'm also sharing office with Xavier, and we're having quite interesting discussions as well. It's quite nice, and many others that I forget. Oh, sorry. So just to remind you, diagrammatic Monte-Carlo, the idea here, what I'm considering is a model, the Hubbard model, on an infinite lattice at equilibrium. So I will only talk about an equilibrium here. And the idea is to construct a perturbation series for an observable of interest, say in powers of the interaction U. So this can be double occupancy, density, a green function, anything. It has usually quite a nice diagrammatic interpretation. For example, for something like pressure or log Z, this would be the sum of all connected diagrams. Now, let me already mention that in general, the series for an observable doesn't need to have an infinite convergence radius. Generally, it has a finite convergence radius because of poles in the complex plane for that observable. Now, in practice, to compute these coefficients, we use a stochastic approach. And then there are two challenges. So the two challenges we're facing is, well, first of all, we need to actually compute these coefficients. And this comes with a fermionic sign problem. So this is the first thing that we need to address, and which limits the number of coefficients that we can actually compute. And even if we do that, we still need to resum the series, because, like I said, the observables doesn't need to have an infinite convergence. I mean, the series may have a finite convergence radius, so we need to find ways to actually evaluate this at the point of interest. So to address the first challenge, in the past years, this is a bit let's say, the story. Usually these coefficients have an easy or a clear diagrammatic representation, and originally the way to compute these coefficients was to actually create a Monte-Carlo to stochastically sample the diagrams of this series. So you were stochastically sampling topologies and also changing internal vertices. This is what used to be called Diagrammatic, and you could typically compute 6 to 7 orders. Now this comes with a sign problem, and it has two origins basically. The first one is, well, you have an integration over internal variables, and this may change the sign of the contribution. So this is the first origin. And another one is the sum over different topologies, even for a fixed set of internal vertices. So to address that second origin of the sign problem, there's been quite a bit of progress with the idea that we could, well, just sum all the topologies for a given set of internal vertices. Now, if you do this the brute force way, of course, you have to sum all topologies. There's a factorial number of them, and this is extremely expensive numerically. But it's been shown, and this is work by Ricardo in 2016, that you can do that in exponential time. So it's 3 to the power n or n squared 2 to the power n. There's different ways to do this, but they're pretty much the same for the typical orders we can compute. And the idea is to do a recursion. You compute determinants. If you compute one determinant, you get a family of diagrams which is too large. You get also disconnected diagrams, and then you recursively take out those disconnected diagrams, and this recursion costs this typical exponential power. And this has then been generalized with work, for example, with Lattice, but also with Ferrero and Genia to 1 pi observables. And with this, we can now typically compute 10 to 12 orders. So this is a way, I mean, to reduce the variance and to compute more of these coefficients and more precisely. Now, the second challenge is actually to resum these series. So let me try to illustrate this here. So if I take a typical observable, let's say the density, and here I take a case where I can solve things analytically. So I look at the density for a Hubbard atom. This is just an isolated site with a U term in there. And I look at how this quantity looks like in the complex plane of real part of U, imaginary part of U. So this typically has poles like this. And the question is, well, imagine the physical value I'm interested in is here. How do I get the value there? Well, in terms of series, the convergence radius is controlled by the nearest pole, which is, say, this one, or this, I don't know which one it is here, or this one maybe. So evaluating here, I mean, the value here is beyond the convergence radius, so you need to do something about this. So there's been quite a bit of work on trying to do conformal maps or Padé approximants, integral approximants, different ways in different groups that try to change the structure of the pole, move them away in a way to get your answer at the physical value of interest. So that is one approach. This is if you want post-processing. You already have your coefficients, and then you work on the series. Another approach is to change the starting point instead. We have some freedom, and I'll discuss this more in details later, but we have some freedom, for example, in the Baire propagator. So instead of starting with this Baire propagator, which has this usual form, we can artificially shift, say, by some constant, say an effective chemical potential. And this changes the actual series you're computing. This, you have to introduce counter terms. I'll explain this more later. But this now changes the starting point, and it changes the structure of the series and the position of the pole. So just to illustrate this, if this will work. So this is now, again, a Hubbard atom. This is the self-energy taken at its first Matsubar frequency, again, in the complex plane of U, imaginary part, real part. And this is where we want to look at the self-energy. And originally, we have poles that are too close to the origin to do this easily. If we tune alpha, this parameter here, and let it take different values, you see that the pole structure changes with alpha. And by taking a clever value of alpha, say somewhere here, for example, well, we can push all the poles away and evaluate this at the physical value of interest. So this liberty has been used in several works in real time by Rosario Profumo and others, and we did this at equilibrium with Wei Wu and then in further works as well. And so a clever choice of this parameter can help either resum the series, or maybe sometimes even you don't need to resum the series, but just evaluate directly. So this is what I want to discuss basically today, is a freedom in starting from a different non-interacting, if you want, or taking different starting points to construct the perturbation series. Of course, there's lots of activities in these other things too, but I'm not going to address this. So where do we stand? So I'll have two slides here trying to just give an idea of what it is we can do, I would say today, for the Hubbard model. So one thing we've been interested in, obviously with an interest for the cuprets, is to address the pseudo-gap region. So this is space diagram as a function of temperature doping, and in the cuprets, you know, there's this region, pseudo-gap region, where there's nodal antinodal differentiation with well-behaved quasi-particles at the node, close to pi over 2, pi over 2, and the destruction of the quasi-particles close to the antinode. So this is a problem we wanted to address. And so we've been looking with Wei Wu, Genia, and Antoine for parameters that would allow to address this question. And this is more or less what we could achieve. So U 5.6, a T prime, which is relevant for cuprets, temperature 0.2 T, and about 4% doping. And this is more or less what we can stabilize, but this is already enough to see signatures of the pseudo gap. You see it in the spectral function. This is computed from Diagrammatic Monte-Carlo. So we see nodal antinodal differentiation. That's the corresponding self-energy, which is stronger at the antinode. You can see it here following a cut. And you clearly see that this is the self-energy, first Matsubar frequency. And you see that it's more negative at the antinode than at the node here. And here, actually, we even have a way to compare to extrapolations of DCA, and those two methods really agree, except here we really have a very fine K definition. So that's more or less where we stand. But as soon as we try to lower the temperature, resumming the series becomes really very tricky. So this, as soon as you enter a more correlated regime here, the series starts to be really difficult to solve.
So, excuse me, Michel, may I ask a little more about that?
Yeah.
Because, in fact, I would have thought that the Hubbard model is strongly correlated over a wider range of dopings and temperatures, and when you hit that regime, it's when the correlations start to have an interesting spatial structure.
True.
So, but is it the spatial structure which is making it awkward for diagrammatic Monte-Carlo, or if I really, even on the, in the regime where single site is good, are there convergence issues?
No, there are convergence issues even when the things are local. So it's not necessarily just correlated to the spatial correlations. It's just, I would say, having self-energies that start to be large, even if they're local. But admittedly, we've not scanned many parameters. Essentially, this is what we did, and for now, there's been no systematic studies as a function of the opening temperature and U. This is pretty happy. So Genia will talk a lot more about this tomorrow, but there's also been quite a bit of work by Fedor, Aram, and Genia on the half-filled Hubbard model, which is a good test bed for diagrammatic Monte-Carlo, where we think it would be working best. And again, I'm not going to talk much about this, but I just want to make the point, this is the diagram here as a function of temperature and U. And so if I fix the temperature and move in U, I first have something which is a well-behaved Fermi liquid, and as I go to stronger interactions, I have antiferromagnetic correlations that start to be long, and I enter a regime which is more insulating-like. Now, in terms of the method, if you try to do the resummation, this is what's illustrated here along this cut here. This is the self-energy, again, taken at the first Matsubara frequency, at the node and at the antinode. This is why there are two curves. And we're using different resummation techniques here. And you see, for some time, different resummation techniques agree. And these arrows are when we enter this insulating-like state. But quite quickly after we enter this insulating-like state, different resummation methods disagree, and it starts essentially to be impossible to do the resummation. So very quickly after you enter correlated regimes, the method starts having issues.
And this region is around 5.5.
The value here, yeah, this is about 4.5, 5, or something like this. This is where it gets pretty tough for that value of the temperature, which is 0.25. So our interpretation, I think so far, maybe in both cases, is that if I go to the complex plane, I typically have something like this for the Hubbard model. At negative U, it seems to always be a pole at about minus, say, 5, which is probably just the superconducting state, and this is signaled by a pole. But then on the positive side, close to where we want to evaluate the function, there seems to be a pole which is very close to the real axis, and this makes the resummation really difficult. So this is typically what we're facing when we do these direct approaches, and the current limitations in my view. So we explored new starting points to see how we can improve this. And sorry for the different names, but you'll have to remember them. So CDAT is what we used to be doing. This is connected determinants. This is using determinants to take out disconnected diagrams. And we typically have pole structures like this. And actually everywhere on the real axis, you do have the solution you're evaluating there corresponds to some physical system, maybe at a slightly different chemical potential, but this is a true solution, and we have this pole close to the real axis. The two things we explored, one of them is called RPA-DET, because it starts from an RPA-like solution. And I'll try to argue there that what happens is we don't really, on the real axis, because of changing the starting point, we don't really address the physical system there anymore. It's really just physical at the one value that we're interested in. Okay? And this allows to change the pole structure in a given way that I'll discuss more in the details. Another approach is RDET, this Renormalize Determinants approach, which changes the Baire propagator in some way. And there, only 2 points are physical. And again, this reorganizes the pole structure in a way that I'll describe a bit more. So I'll start with RPA-DET and then switch to the other one. This is really what Felix has been talking about, so I'll be repeating a bit the story. But the idea is basically to dress the propagator within RPA. So you build up a ladder like this, and you use the renormalized vertex, which is U plus this ladder. So there's two ways to do it. One way is to use the Baire propagator and this renormalized vertex and to construct the perturbations around this. Of course, you have to, that's what also Felix was saying, you have additional terms that you have to balance, to eliminate. Another way, and this is what we actually did, is to do a self-consistent RPA calculation where you also modify the Baire propagator. So you do a self-consistency on the Baire propagator, a bit in the GW spirit, and use this as a starting point. And now you have a modified Baire propagator and also a modified interaction vertex. Okay? And the trick is that still you can do this within the framework of determinants, as Felix was saying. And so just for aficionados, I'll spend 2 slides trying to explain this, but this is getting a bit technical, so don't worry. Again, the way we compute these coefficients is using basically Wick's theorem. So we compute for every coefficient some product of determinants that I can write like this. I can do this, I can write the product of these 2 determinants as the determinant of a product matrix, which I can write in different ways. It doesn't really matter here. And in this product matrix, the vertex, it appears in the following way. So I do the multiplication of the 2 original matrix. So I get this, which is a product of 2 non-interacting Green's functions. These are the entries of my matrices here. And I can represent this as something like this. It's like 2 legs that stem out from an interaction vertex. And so we're going to do RPA. What I basically do, I modify this interaction vertex into the RPA propagator, which has a U here, and which has my ladder here. It has the ladder, and then it has these 2 outgoing G0s. So if you look at that with a bit of imagination, you'll immediately recognize a lobster. So this guy we call a lobster. And it's a tricky animal because there's an internal vertex here that you have to integrate over. You can do this by Monte-Carlo, but it turns out to be much better to actually do this integration of this internal vertex explicitly. But that's kind of tricky. Because this lobster of sorts is quite heavy. It depends on 2 external vertices, which is, lattice site plus whatever you use to encode your imaginary time, like Chebyshev coefficients. And you have to integrate for every pair over this internal vertex. So this turns out to be very, very heavy. And so the way we do this is we do it explicitly for a smaller grid of extent. So within, say, a 5x5 cluster, we actually do the integration exactly. And this is what the Monte-Carlo samples most of the time. And when we get out of this, then we do the computation on the fly. This is a lot slower, but it only happens every once in a while. So all in all, it balances out. Now, by doing this, I modified the propagator. So I need to compensate for this. And this I can do by removing the diagonal of this product matrix, because that is the one that carries those RPA bubbles. Of course, there's a catch in that. When I remove the diagonal, I introduce non-physical diagrams. This is what Felix was saying earlier, especially diagrams that have an interaction vertex, but then only 2 propagators coming out of it instead of 4. And this only obviously happens at order 4, so it takes some time to be discovered. And this was found by Takahiro, Goe, and Felix. And the cure for this is to, or possible cure at least, is to introduce auxiliary spins on all vertices and sum over them. So when you have only 2 incoming Green's function like this and sum over this vertex, it cancels out and those non-physical diagrams disappear. So this comes with an extra cost, which is summing over all these auxiliary spins. Okay, so much for the RPA and for aficionados. Now go to the next method, RDET, which is basically a generalization of what I was telling earlier, of this freedom to change the Baire propagator. So let me just say how this exactly works. How do you counter the terms that you introduce when you do this? So imagine my original Baire propagator. I write it like this. It's my original propagator. I remove an alpha and add U alpha over the physical U I'm interested in. And this is my expansion parameter. You see, when I evaluate this at the physical U, the alphas cancel out, and I'm back to the original series. Now I do an expansion, the geometric series for this, and I get terms, which is this modified propagator, G0, minus G0 alpha G0, plus G0 alpha G0 alpha G0, and so on, which I can write in a Dyson-like equation like this, by G0, and those alpha terms that correct the modification that I brought to the Baire propagator. So in diagrammatics, say for G, now it looks like something like this. It's your usual diagrammatics. Here, a tadpole insertion, 2 tadpole insertions, a pair bubble, and so on. But then there are also diagrams which have those alpha insertions. And actually, it's quite nice because every time you have a tadpole insertion, there's an equivalent diagram which has an alpha insertion. So a clever choice, it turns out, for alpha is to take its value to be that of the bare tadpole, such that all tadpole insertions disappear. And this is actually nothing but starting from mean field. When you do this, it's exactly like doing mean field theory and starting your expansion from mean field. So this seems to be always a quite clever choice for alpha. So we want to bring that to the next level and take a bare propagator which has more freedom, which also has this static alpha shift, but which has one more shift, which is now a frequency and possibly k-dependent shift delta. And it's the same story. If I do that, I have to modify my propagators in a way with counter terms that have those delta insertions in there. So now in the diagrammatics, I have propagators like this, the usual diagrams, but also diagrams which are propagators with the delta insertions like this. Okay? And actually, if I tune my alpha, I can get rid of all tadpole insertions in here as well. So this is what we call renormalized determinant approach, or that. And you can show that for a given set of vertices, you can do that exactly using determinants. And this is something that Riccardo Rossi will describe in his talk on Wednesday. So I won't go into the details of this. Then comes obviously the question, so what do I put in this function? Because alpha used to be a scalar, that was nice, but now I have a function. So what do I put in there? Well, for now we're just trying things. So we've basically been trying two things. One is to take a function which has a bit of a gap, right? It's something like delta over this, which is basically a pole. And basically, actually, we turned out that the most common thing, or the best thing, is to use beta 0, so just something which is like delta over I omega n, and we scan for different values of this parameter delta tilde here. Another thing we tried is to, because there's not one in the room, so I have to be a bit careful. So I use self-energy from DMFT to try this, and you'll see that it turns out to be a very good choice. And then we can compute different observables. I'll show lots of results, mainly for the density, but we can compute double occupancy, Green's functions, self-energies, and so on.
And Michel, just
yes?
One comment for the previous thing. When you say hybridization function with a gap, you mean a hybridization function which generates a gap in genome?
Yeah, that's what I meant, sorry. Yeah, my bad.
Because as such, it has
a... No, you're right. It generates a gap in the bare propagator. That's what I meant, yes, sorry. Right. Indeed. Okay, so let me show you some results. Now, but maybe before results, just about the complexity. Of course, this comes with a certain cost. So these methods are a bit heavier than the original CDAT. So this is the time to the one Monte-Carlo step as a function of order. So the CDAT scales at 3 to the power n, or n squared to the power n, which is this scaling here. RPA dat, as Felix was mentioning, goes like n cubed 3 to the power n. So this is indeed the scaling that we start to see here at orders 9. The RDAT comes at a slightly higher cost, which is n cubed 4 to the power n, which is this blue line here. So you see it's heavier, but if I look at the relative error bar, so this is what I'm showing here, the relative error bar as a function of order for, if you want, calculations that have the same running time, you see that actually, okay, RPA-DAT has a slightly bigger relative error bar, CDAT is here, but RDAT actually has a smaller relative error bar, even though it's a lot heavier to compute. So the variance is reduced. So there are several reasons for this. One reason is probably that, well, we're already resumming things that have a smaller variance problem in the first place. But another thing which we observe is, if I look at the spread of the typical diagrams that I'm sampling, or the vertices that are in my perturbation theory, this behaves a bit differently according to the method. So these columns are different temperature. This is beta 5, beta 10, beta 20. First line is for CDAT. What you see as you lower the temperature is that your diagrams, your vertices, they typically spread out. And obviously, this doesn't help your variance. When you look at this for RDAT, you see that the dependence in temperature is very weak. Actually, the diagrams don't spread too far out, and this is also helping you having a better variance. Same thing for RPA-DAT. Except here for now, we are reaching a bit the limits of the method. So at beta 20, we could not really get the thing to converge. Yes, Olivier?
What is plotted exactly? That's an histogram of the point.
So yeah, that's a histogram of where of the typical distance of the vertex from, say, the center of gravity, if you want.
Yeah, in space.
In space, yeah, sorry.
Okay.
So that's space here. Okay, so now results. So first on the Hubbard atom, where we have a good benchmark. So these are the three methods. Now see that in red, RDET in blue, and in green, RPA-det. So this is taken at, well, beta U equal to 8, and some chemical potential here. If I take the original CDET, you see the series blows quite crazy, and there's no way, at least no easy way, that this can be resummed. If instead I do RDET or RPA-det, so this is a blow up. One thing you see, if I start with RPA-det doesn't have those oscillations. Actually, it really looks like RPA-det provides a series which would eventually be, I mean, it's a converging series. So it looks like we're inside the convergence radius, but there are those slow oscillations, so it actually takes quite a number of orders maybe to finally reach the value, but this can still be resummed here. RDET instead has some oscillations, but it turns out to be, well, here it actually goes to the result, and it's very easy to resum, so it's compatible.
And that was RDET with the starting point?
Good question. I think this was for something that generates a gap. That was not, yeah, there's no DFT there. But I don't remember the value of the delta there. Oh, we also computed double occupancy. This is now for, well, actually it's in red, but this is RDET. Correct me, Ferrero, if I'm wrong.
It's RDET.
It's RDET. Sorry for the color.
It actually says RDET.
Blue. Oh, it says, yeah, right. Good. It's just a color. And it also works quite nicely here. Okay, now if I switch to the more interesting lattice Hubbard model. So again, we look at those parameters that are the ones that we've been working with quite a bit to address the pseudo gap. So the limit used to be beta 5. And these are now the partial resummations of the series as a function of orders. And what we're looking at here is density, beta 5. And these curves are for different choices for this gap that we put in the hybrid, I mean, for this parameter in the hybridization function. And so with CC, delta 0 is just the original CDET. It's this black line here, and you know, in the end, it really goes a bit erratic, and it's something that is really hard. You can resum it, but it's really hard here. But if you tune delta, you see the behavior changes to something which is more oscillating, and eventually to something which would maybe go with a bit slowly to the right answer. So there's an optimal value where the thing is easiest to resum, and we can show it here. So these are for different values of delta, the resummation, the value for after resummation with an error bar. And you see there's an optimal value where you can get a small error bar here. And this is actually compatible, I'll talk about it later, with RPA-det, which is what you obtain here in green. So those two things agree. Now you can lower the temperature, which we couldn't do before. And still, by tuning delta, you can get series that are nicely alternating and that you can resum. And so you have a plateau of values that are compatible. And eventually, when this delta starts to be too big, I think there we have truncation errors because of the limited number of orders we compute. But still, we see this plateau and a reasonable error bar here. And beta 20 is still a bit the limit. We can push this a bit more. But we still see sort of a plateau at first, and then it goes away with reasonable error bars. So we can really now address a beta 20 for the same model, which was really completely out of reach before. So some results here where we compare RPA-det now, which is the green curve, with a well-chosen RDET with the optimal parameter. So again, this is density now for beta 10. And so it's quite interesting. So again, CDET is this curve, which is really quite hard to resum here. The blue one, sorry, is the RDET with the good parameters. So this is something that you can resum quite nicely. And RPA-det has it's a different behavior. It doesn't have this oscillatory behavior. It seems like it's actually going again to the right value, but it would just take a couple of more orders to get it. And then here on this plot, I also have, this is the violet one, the DMFT. And this turns out actually to be the nicest one. I mean, if you have a trained eye, you see that this is actually something which is quite nice to resum. It seems like it's just one pole on the negative axis. And we can even push this to beta 20 here and compare. And again, DMFT sounds to be a really good choice. You computed 10 orders here, and it's something that we can still resum all the way down to beta 20. So here's our take on what's happening in the complex plane now for these different methods. If I think about RDET, we get those typical, so say taking the DMFT point, we get those typical series which are alternating here. What this seems to be saying is that we went from something which had a pole close to the real axis on the positive side and something on the negative side to something where whatever was close to the real axis on the positive side seems to have disappeared or to be further away, and we're just left with something on the negative side. And this is something that is easy to resolve. So that's what seemed to be happening within RDET. And we're essentially, if we look at divisible convergence radius, pretty much on the convergence radius where we want to evaluate the series. In the RPA det, there it really gives the impression that actually the series is converging. So there's a convergence radius larger than where we want to evaluate, except that it would maybe take a bit more orders to actually get there. So this is how we think that poles may be reorganized in the complex plane using these two approaches. So that pretty much brings me to my conclusion. Well, what's this? I don't know. So taking those new starting points really looks like a promising route to climb, and this is just the beginning of this exploration. Of course, there's many deltas to look at, and so it looks like this is quite encouraging. And I would say that right now, what we can reach is U5.6 and down to beta 20. We also tried U7 and beta 10, which was also working. But the main thing there is it doesn't look like there's something that is really blocking us to go further. Unlike what we used to see with earlier, it really looked like going just a bit further was already impossible. Here it seems like we can even push this a bit further. So that's where we stand now for dopings about 5%. So the conclusion is those two approaches, even though, sorry about that, which should be down here, they have an added complexity, but they yield more and better orders. The variance is more under control and than CDAT, so this is quite important. And so, yeah, the next thing to do is obviously explore other possibilities for delta. For example, we might even want to refeed the solution of RDET into itself and try something like this. And we also mentioned that we can actually extend what we did to computing the self-energy directly with no extra cost. And yeah, maybe just mentioning that we're trying to also put this in a code that is quite versatile and that can be at some point become something like a library. So there's also an effort in this direction by Ricardo and Ferrero in particular. And well, with that, I would like to thank you for your attention.